we welcome to Monte Carlo week for MTV Nest this summer. Today we will have an introduction to Monte Carlo led by Dr. Shaun Clarke, who I'll introduce in a moment. And tomorrow we'll be talking about simulating radiation detectors, building upon this lecture. And this Thursday we will have a special talk from scientists from Los Alamos National Lab on nuclear data and MCNP, which is a code you'll hear about in the next couple of days. Sorry, one thing in the chat.
Okay, Flynn, I think we can start, but something happened and now I can't share my screen. So can you turn?
Yeah, it's because you got demoted from host. Sorry, I will make you a co-host. So sorry, we can't turn off the entry notifications, but I'll make sure to take care of those while you're going.
Sounds good.
Yes. All right, there we go. So yeah, today Dr. Shaun Clarke will be talking to you about an introduction to Monte Carlo. He is the MTV Associate Director and an Associate Research Scientist at the University of Michigan. He has been working with the group here at the University of Michigan for 14 years and specializes in Monte Carlo simulations for radiation detectors. With that, please go ahead, Dr. Clarke.
Okay, thanks, Flynn, and welcome everybody to this week of the MTV Summer School. So as Flynn said, I'm going to give an introduction to Monte Carlo. I'm going to talk about what the method is, how it's implemented, talk a little bit about random sampling, and of course, give you many examples that I hope will make clear what this method is and how it's used. So if you have questions during the lecture, please drop them in the chat, and I'll address them kind of as we go or at the end, depending on the nature of the question. So with that, let's get started. So what is the Monte Carlo method, the origin of the Monte Carlo method? Well, it's been around since the Manhattan Project. So in the early 40s, during the Manhattan Project in the United States, I think we had a very nice lecture on that from Alan Carr a few weeks back. There were discussions about using the supercomputer at Los Alamos National Lab, which was called ENIAC. There were discussions about using that computer for what was then called a method of statistical trials. And of course, this method was meant to be used to support the design activities going on during the Manhattan Project. So you can see here at the bottom of the slide, the three folks who are credited with the kind of this invention of the Monte Carlo method, so to speak. Stan Ulam at the far left was the one who originally made this suggestion to use this supercomputer for these statistical trials. The guy in the middle, Nick Petropoulos, was the first one who coined the name Monte Carlo, which of course comes from the famous gambling city. And John von Neumann, who is the fellow at the far right there at the bottom, was the one who originally developed the first Monte Carlo computer code. So with that said, what is the Monte Carlo method? Well, you can see the word Monte Carlo used all throughout publications in science and engineering. But if you look through a survey of literature and try to find a simple definition, in fact, it can be quite difficult to find a simple and concise definition that captures all of the nuances that are inside the Monte Carlo method. So what I have here on this page is a survey of definitions from a variety of references, textbooks, and journal publications, where some leaders in the field have done their best to define the Monte Carlo method in a simple and concise way. I'm not going to read them all to you, but if you kind of scan these various definitions, you can see several words that are common throughout these definitions, words like random or statistical, mathematical problems, method, these types of things. So while it can be difficult to define the method clearly and concisely, it's suffice to say the Monte Carlo method is any method that involves sampling from a large number of statistical trials. Generally speaking, you're going to use that method to solve a problem. So in fact, I think the first definition here on this slide is probably my favorite, where it's any technique that's using random or pseudo-random numbers to solve a problem. That's, I think, in essence, what the Monte Carlo method is. And throughout the lecture today, I'll talk about how that's done and walk you through some examples to show you what it looks like in practice. So first, we have to understand a few definitions like random sampling and pseudo-random numbers. The distinction here is one between random numbers and pseudo-random numbers. Random numbers are those that are truly random, whereas pseudo-random numbers are actually a sequence of numbers. It's a recursive sequence of numbers where each pseudo-random number depends mathematically on the number before it in the sequence. However, they're generated in such a way that they appear to be random, meaning that when you perform various statistical tests on them, the numbers behave in the same way that a set of truly random numbers would. And for the purposes of a Monte Carlo calculation, these pseudo-random numbers have to satisfy these criteria here at the bottom of the slide. So they have to be positive, real numbers that are uniformly distributed on the interval of 0 to 1. So when you're using random sampling in Monte Carlo, it's convenient, and you'll see why later, that these numbers are normalized such that they exist on the interval of 0 to 1. So again, random numbers are at the core of any Monte Carlo calculation. We can't reliably have a set of large real random numbers. So because we want to implement Monte Carlo on a computer code or computer software, we use pseudo-random numbers. And these numbers are generated using statistical recursive relationships, where every number that you're generating depends on the number before it. And there are several random number generators that exist. I'm not going to go through those in detail today, but a quick search online will reveal to you several of the more common pseudo-random number generators. And you'll see that the period of these generators, meaning how many numbers can they produce before they begin to repeat themselves, is very large. It can be on the order of 10 to the 18 or even more, which is sufficient to use these numbers as random numbers in a typical Monte Carlo calculation. So random numbers are one piece. The other piece that lives at the center, so to speak, of any Monte Carlo approach is what's called the central limit theorem. I'm not going to go through all of the statistics here. I want to give a more broad overview, but I didn't feel like I'd be doing the method justice without at least mentioning the central limit theorem. And what this theorem states is that the sample mean is asymptotically approaches a normal distribution if the number of trials is sufficiently large. So what this theorem does is allow us, when we're doing a Monte Carlo calculation, to use this normal distribution to which the distributions converge to produce confidence intervals. So 1 sigma, 2 sigma, 3 sigma confidence intervals that allow us to not only produce a sample mean using a Monte Carlo method, but also to express an error bar on those means, or a statistical error bar on those means that are produced by the method. So anytime you run a Monte Carlo calculation or solve a problem using a Monte Carlo method, you will produce a mean value, which is kind of the answer that you want, whether it's like a flux or a dose or what have you. You'll get a mean value, as well as a statistical uncertainty with that mean value that represents how well the sample mean is converged to the true mean that you're trying to calculate. Okay, so back to random numbers. I've said everything here at the top. At the bottom are some common algorithms that get used to produce these random numbers: mid-square, multiplicative, congruential, mixed congruential. You can find random number generators in any type of software that you typically use, whether it's Python or MATLAB. Even Microsoft Excel has a random number generator. So these are all available to you, and you can actually write some pretty efficient Monte Carlo calculations using the random number generators in things like Python and MATLAB. This is a cartoon I like to show. It shows this notion of randomness where when you say random numbers, people kind of have in their mind this picture of numbers that are all different and all over the place. But if they're truly random, you're just as likely to get the same number 6 consecutive times as you are to get 6 different numbers, because each sample in and of itself is indeed random. Okay, so we have our random numbers. What do we do with those random numbers? So I'm going to start a little bit zoomed out in general terms, and then we'll go into some examples. So we're going to assume that we want to sample some physical quantity of interest. It can be an angle or a distance or something like that. And we're going to assume that whatever physical quantity we're trying to sample has some probability density function called little p, lowercase p of x. And because this probability density function is a PDF, it must satisfy 2 particular properties. Now, one of which is it has to be normalized over the entire domain. So whatever space the variable x occupies, in this case, we're just saying 0 to infinity, and whatever space that variable x occupies, integrated over all of that space, you must return 1, which means, in essence, something must happen. So the probability must integrate to 1 over the entire space. And it must also be positive definite because it's a probability. So if we have this probability density function, or PDF of x, the other thing that we need if we're going to perform random sampling is something called a cumulative density function, which is typically denoted as uppercase P of x. And this function is obtained directly from the PDF by integrating it from 0 to x. So if you were to take this integral from 0 to x, p of x prime, you'd return a function that is bound in 0, 1. This is essentially a cumulative distribution of all the possible values of p of x. So the terminal value of uppercase P of x is 1 because the PDF is defined as integrating to 1. So if we have this CDF, or capital P of x, we can use this to perform random sampling using a technique called the inverse transform method. So if we have our CDF uppercase P of x, if we integrate that, that is defined as the integral 0 to x, P of x prime dx prime. If we set that equal to a random number, called c in this case, if we set our CDF equal to a random number c and we invert it, we can then get an expression for x as a function of c. So whatever this variable x was, it's a physical quantity we want to sample. By doing this mathematical operation here and inverting this relationship, we can express this variable x as a function of a random number c. And because this was a normalized PDF, and because c is defined as a random on 0, 1, we can use this process to sample a unique variable x from each individual random number c. This process of random sampling is known as the inverse transform method. There are other ways to randomly sample because, as you can imagine, some functions p of x are not directly or easily integrable. So you can do things like a table lookup method or rejection method. But in a case where this p of x can be integrated and this function can be evaluated analytically, this inverse transform method is a very convenient and efficient way to randomly sample values of x from this PDF using a set of random numbers. So that was all a little bit esoteric. I want to show you a few examples here of what this looks like using some experiment or some examples of increasing complexity. So the first one is the throw of a die. So we're going to consider, for this example, the tossing of a single fair 6-sided die. Okay, so when I say a fair 6-sided die, I mean a single die with 6 sides, and the outcome of all 6 sides is equally probable. Okay, so the outcome 1, 2, 3, 4, 5, 6 is equally probable and is equal to 1/6 on any given side. So if I asked you, what is the average outcome of a single toss of a single fair 6-sided dice? A lot of you probably know it. It's 3.5. You can calculate it analytically, or you could compute it experimentally. So if you take this set C sub 1, where these little n's are the outcomes of the various throws of the dice. So say you threw it 10 times, 100 times, 1,000 times. Eventually, if this set of outcomes in the vector C here was large enough, you could compute the average of the outcome of tossing a fair six-sided die. So you could do this experimentally. If you had some dice and some patience, you could compute this average by performing so-called manual Monte Carlo. We're just rolling the die enough times to get a statistically reliable estimate of the average. But what if we don't want to do that? What if we don't have time and we want to just simulate those outcomes? We would need to perform random sampling. So if you wanted to do this through simulation, here's kind of how it would look. So your goal here would be to simulate a large number of throws of a die through generation of random numbers. And that can be done again, Python, MATLAB, whatever you have access to. So to do random sampling, again, we need two things. We need a PDF and we need a CDF. PDF is probability density function, CDF cumulative density function. So in this case, because the outcomes of our dice roll or dice toss are discrete, this is going to be an example of a discrete PDF. So there's 6 possible outcomes, and I've told you the dice is fair. So you know that each probability piece of I is equal to 1/6 because the outcomes are equally probable. So that's the PDF. That's pretty straightforward. To get the CDF, you have to perform this cumulative integral that I showed a couple slides back. In this case, because our PDF is discrete, this cumulative integral gets rewritten as a cumulative sum. So P sub 1 is 1/6, P sub 2 is 1/6 plus 1/6, so on and so forth, until you've summed over all 6 outcomes of the die. This is easier to understand visually, I think. So this is what it looks like. So these are our 6 possible outcomes on the 6-sided die. And we know that each probability is equal to 1/6. So you can see that here. And what's growing along the y-axis here is our cumulative density function. Okay, so big P1 is just lowercase p1. This is a typo. Big P2 is P1 plus P2. Big P3 is P1 plus P2 plus P3. P4 sums up to P4, P5 up to P5, so on and so forth. So this set of values here would be the discrete cumulative density function for the toss of a fair 6-sided die. So we have our CDF, and now we want to perform random sampling. So the way this works is we would take our random number generator, whether it's MATLAB or Excel or what have you, and we would request that generator to send us a random number. And it's going to give us a random number that's normalized on 0, 1. And we would just map that random number to the values of our CDF. Okay, so if we request a number from our generator and it spits back the number of 0.4, for example. 0.4 is going to land here in this band between 0.33 and 0.5. 0.4 is going to correspond to an outcome of 3 on our dice. If we request another number from the generator and it returns, say, 0.9 up here, that lands in this band, that's going to correspond to an outcome of 6 on our dice experiment. And we could do this as many times as we want, requesting random numbers from our generator, seeing which band they fall into, and mapping those bands to the various outcomes of the dice toss. So we can do this. We can create this set of die toss outcomes using random sampling in this way. And if we do that enough times, instead of having a vector of true experimental outcomes, we have a vector of outcomes that are dependent upon the various random numbers, and we can compute the mean in exactly the same way we computed it using the experimental approach. Okay, so that was the discrete example. I want to move on to a continuous example. This is something called the hit or miss experiment that you can find in any Monte Carlo textbook, where our goal here is to compute the surface area of a plane, in this case called S, a plane with a complex shape. Okay, its shape is such that we cannot just compute the area. So our goal is to compute this area using a Monte Carlo method. And you can think about this problem visually. So if you had this, this square, say, with side b minus a and d minus c, and where that square fully encloses the surface S, whose area you want to compute. So by containing our surface S in a shape of known area, we can compute the surface area S by Monte Carlo through essentially called a hit or miss experiment, which essentially boils down to, you can imagine it like throwing darts at this board. Okay, so if you had this surface in front of you and you were to randomly throw darts at this board, say, some of the darts would land inside S, the green region, some of the darts would land in the purple region. And if you define lowercase n as the number of darts that land in the green region, the area of the green region is just that ratio, the darts that land in the green over the total area, over the total number of tosses, sorry, times the area of the known rectangle, the purple area. So it's the fraction of darts that hit the green of time total area would give you the area of S. Okay, so we can do this mechanically. If you were to have this sort of scaled map of this area S, you could physically, throw darts or drop things on it and count the number that would land inside, but that is not very elegant. So what we want to do is compute this using Monte Carlo. So to compute this using Monte Carlo, we need to simulate the outcome of dropping points randomly inside that square AB. So to do that, if we assume a two-dimensional situation here, we need to generate coordinates x sub I, y sub I that land inside of this rectangle, whose, I'm gonna go back real quick, whose side lengths are A to B on the X and C to D on the Y. So this can be derived using the inverse transform method I showed a few slides back. I'm not gonna go through it here, but even visually, you can see if you want a value continuous on X here, it's gonna be A plus a linear interpolation up to B. And that's what we come up to here. So your minimum value here, if your random number comes out to 0, the min value of X is A. If the random number gets sampled to be 1, the max value of X is B. So you can see from this relationship that assuming the random number C is bound on 0, 1, this X sub I will be bound on A to B. Similarly, if the second random number eta is bound on 0, 1, the resulting values of Y will be bound on the interval of C to D. It's important to note that in this case, we're randomly sampling pairs of random numbers. So we need to sample of coordinates. So we need pairs of independent random numbers to do this sampling. So that's why we have two different letters noted here for these random numbers. So a couple of comments on this one. Obviously, if it's a skilled player that's throwing these darts or dropping these items on the surface, it's going to bias the solution, right? So that is to say, if you're trying to estimate the area of S, you shouldn't try to aim at S, so to speak. In other words, the coordinates X and Y must be uniformly distributed over that surface area. Or in other words, the darts must be thrown randomly to get back to the analogy. And that's kind of what we say down here in other words, right? So to make this hit or miss experiment valid, the endpoints must be chosen uniformly over the entire rectangle, where the rectangle is the shape that bounds the area S, whose area you want to compute. The other thing that's not mentioned here is the efficiency of this hit or miss experiment is related to how closely the rectangle, in this case, bounds that surface S. You can see that visually here. Because we're sampling randoms between A, B, and C, D, if this rectangle were much, much larger than S, only very few of our coordinates would land in S. So to make this method efficient, you want the area, the bounding area to as closely match the surface S as possible. Okay, cool. So that's the two basic experiments or examples I wanted to cover. Let's get on to something a little bit more relevant to nuclear engineering. So in this case, we're going to talk about penetration through a shielding material. So for this problem, we're going to consider a shielding block that is 4 half layers thick. And what I mean by half layer is whatever the energy of the incoming radiation is, the thickness of this shield is sufficient that it will block half of the radiation that's going through it. That's 1 half layer. So in this case, our shield is going to be 4 half layers thick. And we want to estimate the probability that particles will be transmitted through that shielding block. It's fairly obvious to compute analytically, but we want to think about it from a Monte Carlo sense. And in fact, we can solve this problem using 6-sided dice. If we were all in the same room together, I would pass out 87 dice, and we could do this together. But instead, I'm just going to talk you through it, and maybe you can practice it later with your friends or family. So this picture shows a cartoon of what it looks like. So again, we've got 4 half layers here of shielding material, and a half layer is defined as thickness such that half of the particles will be stopped. So there are 16 arrows coming in here. Once they pass through the half layer, it's down to 8, other half layer down to 4, other half layer down to 2, other half layer down to 1. So the transmission probability is quite simply 1/2 to the 4th, because there's 4 layers here, which is 1/16, or approximately 6%. So we can compute this analytically in a very simple way. But how could we compute this? Firstly, with Monte Carlo, but secondly, using 6-sided dice as our random number generator. So we need a PDF and a CDF to do this. And because our shielding blocks are half layers, there are only 2 possible outcomes for this experiment. We're going to assume the particles have 2 fates. They can either be absorbed or they can be transmitted through each of those half layers. And because the probability is 50%, we set half of our die outcomes to absorbed and the other half to be transmitted. Okay, so if you were doing this as an experiment, you could have the whole room of audience members stand up, pass out dice, and you'd have them all roll. And anybody that rolls 1, 2, and 3 would be asked to sit. That would be the outcome of the first layer, and we'd count the number of folks standing, and then we would have the folks that are standing roll again to see if they get absorbed. And we do this 4 consecutive times, and eventually once we've done this 4 times, we would have a few of you still standing at the end. Okay, and if we started with 89 people, which is how many are in this lecture right now, the number of audience members left standing at the end divided by 89, which is what we started with, would be our estimate of this absorption probability, which is fine. But the other question is, what's the uncertainty on this number? So if we did this experiment starting with only 16 people, it's very unlikely that exactly 1 person would be left standing at the end. Maybe there'd be 2 people left standing at the end, or maybe there'd be 0 left standing at the end. So we can estimate the uncertainty on our prediction as 1/the square root of the number of scores. This is a result of the central limit theorem, and you can see that as the number of scores is low, the reliability of the result is poor. Okay, so if we successfully did this experiment with 16 samples or 16 audience members, and we got lucky enough to have 1 audience member remaining at the end, we would get the correct mean, but our error bar would be something like 1 over the square root of 1 or 100%, which is not a good statistical estimate. So to improve the reliability of that result, there's two ways to do it. One way would be just to perform more trials, okay, so have more starting particles, so to speak. The other way is to perform something called particle splitting, which is something that is done in Monte Carlo that allows the transport or the problem to be solved with an artificially increased population, but adjusted in such a way that the mean remains unbiased. So what do I mean by that? What we could do is, after transmission through each half layer, we could split every particle that's transmitted into 2 particles, okay? Clearly that's violating the notion that half the particles should be absorbed. However, if when we do this splitting, we reduce the weight of the particle, so if we split into 2, we reduce the weight to 1/2, and if we include this weight in our calculation at the end, we can preserve the mean while increasing the number of scores. Okay, so the mean gets preserved because of this weight to W to the M power here. The mean gets preserved, and N also increases, meaning that our 1 over root N uncertainty decreases. So this is a technique known as geometric splitting that is very common in many Monte Carlo methods and codes. You can find it in any textbook. And the way it gets used is often for problems like this, where you want to increase your population artificially in regions of interest, whether it's geometric regions of interest or energy regions of interest, and then allows you, again, to reduce your statistical uncertainty on an estimate for a region of interest that you care about. So that's particle splitting. Okay, so I'm going to delve a little bit more deeply into the transport application here and talk about a problem, in this case, kind of a 1D Monte Carlo simulation, to show you how you would randomly sample quantities that are more, say, physically relevant, right? So we've talked about, rolling dice, and we've talked about simple transmission versus absorption. But in this case, what if you have particles that are incident on some slab and you want to know what happens in this transport? You want to be able to simulate more outcomes, right? So in this case, if we assume we have a slab of thickness D, and we're going to give this slab 2 material cross sections, sigma sub S, which is a scattering cross section, which means particles can scatter and change direction, and sigma A, which means the absorption cross section, which means the particles could get lost. If we consider this simple material, the particles entering this slab have essentially 3 possible outcomes they can undergo. They can be absorbed in the slab through undergoing an absorption reaction. They can reflect back out the front of the slab, or they can transmit fully through the slab. Okay, so I want to talk about how we can simulate that and how we can randomly sample the quantities of interest that we would need to perform this calculation, should we be so inclined. This is a visual of kind of what I just said. So to do this calculation, what we need to do in our Monte Carlo space or in random sampling space is to create these particle tracks. And if we think of these particles as neutrons, what we're doing here is simulating what's called the random walk, or how the neutrons scatter around in a given medium. And we want to track the history of these particles as they go through the slab, and we want to tally or count up these 3 outcomes. We want to find out how many of our samples make it through transmission, how many get absorbed, and how many reflect back out the front. So this is just a graphical representation of what we mean by random walk in the Monte Carlo world. Random walk is visually, these various scatterings and directions that particles take in a slab, but phenomenologically, it's just a set of state variables. If you think any state in the Monte Carlo calculation can be defined using these 6 values, which is the 3-coordinate position, the energy, and a 2-coordinate solid angle vector. And if we have this information, if we have these 6 numbers, we know the state of our particle at any point during its lifetime. In Monte Carlo calculations, there's often a seventh state variable here, which is the weight of the particle, which is kind of what I was getting at with the splitting a couple slides back. But apart from that, these 6 state variables can be used to uniquely define that particle at any point of its lifetime in the transport. So if we're going to do random sampling, we need to be able to estimate or sample these various quantities at every step along the way. Okay, and because we're talking about radiation here, which is inherently stochastic in nature, all of these properties are indeed random. Okay, so when a particle is born, its location, energy, and direction can be random. Okay, in some cases, your source has fixed energy, but in general, those can be considered as random. How far will the particle travel before it collides in the medium? That's random. Okay. What type of collision does the particle undergo when it has this first collision? It's random. Okay. In the case of our simple example, it can be absorption or scattering. If the collision is absorption, maybe it makes secondary particles, or maybe it doesn't. Who knows? That's random, right? So we need to be able to simulate all these processes along the way if we want to perform a Monte Carlo solution to this transport problem. So as we said, the phase space of this particle along its random walk consists of a set of 6 variables, 3 spatial, 2 angle, and 1 energy. And in terms of the source, which is the most important step of Monte Carlo calculation, if you're going to do particle transport in any kind of medium, you need to define a source. So what's typically done is we assume separability, which means whatever spatial, angular, and energy information we need to produce the source, we can assume they're all independent of one another. Okay, that's an assumption, may not always be true, but for the purposes of today's discussion, we are going to assume separability in these 3 variables: space, energy, and angle. And it needs to be normalized, okay, because we are going to sample from these. They need to be PDFs, which is basically what's set here at the bottom. So whatever probability we have for these different variables, energy, angle, position, they need to be positive, definite, and their probability needs to integrate to 1. So for the sake of argument, we'll just assume that our source is at a fixed position and a fixed energy, which is fairly common, but the angle of these particles is often not fixed. Okay, so if you're thinking about a radiation source, a point source that you want to simulate, it's often convenient to model those radiation sources as isotropic, meaning that when the particles are born from that source, any direction of travel is equally probable. That's what we mean by isotropic. And the math here on the slide shows you how one can randomly sample the direction of an isotropically emitted source. Okay, so the derivation is mostly written here. I'm just going to walk through it quickly. We want to sample the full direction omega, which is a function of 2 angles, phi and theta. And we essentially, this top line assumes that they're separable. Okay, we're going to assume that d omega is a product of d phi and d theta, so which allows us to sample those 2 angles independently. Okay, second line here is just a convenient change of variables where we're taking mu to be defined as cosine theta, and then down here we're doing the random sampling. Okay, so this is the PDF lowercase p of mu d mu. We're integrating that from -1, and we're setting it equal to a random number. Invert and solve, and we can express mu as a function of our random number c. Similarly, on the right here, if we want to randomly sample this phi variable, we again construct a CDF from P2 of phi from 0 to phi, set that equal to a second random number, C2, invert, solve, and we can express phi as a function of C2, a second random number. So by sampling sets of independent random numbers, phi1 and phi2, we can generate pairs of angles, mu or cosine theta, and phi, which then allow us to define this angular direction vector omega. Okay, so if you want to simulate the direction of isotropically emitted particles from a source, you need two random numbers, and these are the two expressions that you would use to do that. And this is solely based on the inverse transform method that I introduced earlier on in the lecture, where we're taking our physical P of X, or in this case P of phi, and we're creating a CDF from that, setting equal to random, invert, and solve. Okay, so that's the direction of isotropically emitted particles. Once the particles are emitted and they enter our slab, the question is, how far will these particles travel along in that slab? And that probability is a function of the cross section in that slab. Cross section is a quantity that's related to collision probability in a given material or medium. So transport in a medium of cross-section sigma is governed by this exponential relationship, e to the minus sigma times r, where r is just some distance variable, and sigma is the total cross-section in that medium. The sigma dr on the outside exists because this has to be a PDF, which means it has to be normalized to 1. So this sigma dr on the outside is so that this P of r, when integrated from 0 to infinity, integrates to 1. So we take our P of x and we integrate from 0 to r prime, set it equal to a random number down here. Invert, we can express a distance r as a function of random number c, that allows us to sample how far a particle will travel before having a collision in a medium characterized by cross-section sigma. This little substitution down here, we take log 1 minus c. You often see it written as just log of c here on the far right in most textbooks. And that's simply because if c is truly distributed uniformly on 0, 1, so is 1 minus c. So it's just simpler to write it in the simplified form on the right. Okay, so we have particles emitted isotropically, sampled on the previous page. They travel some distance r based on sampling from this page. And then when they arrive at the medium, the question is, what type of collision do they undergo? Okay, so this is a more general form of the cross-section, but in our case, we talked about maybe it's only scattering and absorption, but in reality, the total cross-section in a medium can be a sum of many different reaction types. Maybe it's elastic scatter, inelastic scatter, fission, end-to-end type reactions. Any number of reactions can occur. And if you sum all those possibilities together, that's the total cross-section. Okay, so this is analogous to the discrete PDF we started today with, which was the outcome of a 6-sided die. Only in this case, we have a many-sided die, so to speak, and the sides are not all fair because each of these cross-sections has its own probability. So if we divide this whole expression on the top by the total cross-section, that results in a normalized distribution, which is again our PDF. And if we take a step function from that PDF, discrete PDF, and set it as a CDF, we can use that to sample in the same exact way we sampled the 6 dice outcomes earlier in the lecture. Okay, so if lowercase p sub n is the probability of elastic scatter reaction, if p sub n prime is the probability of inelastic scatter, p gamma is radiative capture. If we keep building this step function, eventually we'll have all the outcomes there, and we can map our individual random numbers that our generator provides to the various reaction types from the cross-section data. Okay, this is the same sampling we used to get the 6 dice outcomes. Okay, I have one more thing I want to talk about in the last 5 minutes here, which is how do we tally these things? So tally is a jargon that's used in Monte Carlo, which basically means how do we get the answer that we want. So sometimes you're doing a Monte Carlo calculation to compute particle flux. Sometimes you're doing it to compute a reaction rate or energy deposition or dose, so on and so forth. These things are all computed in Monte Carlo calculations through essentially counting events that occur. Okay, and that's the jargon for that is called a tally. So I want to just show you the three common scoring methods that are used in Monte Carlo calculations and how they can be used to count up the quantities of interest. So the three scoring methods are here at the bottom: collision density scoring, track length scoring, and surface crossing or plane crossing scoring. And what do those look like? Well, there are again many things you can tally in Monte Carlo. If you think about a current tally or how many particles are kind of entering a region, that will be done typically using this surface crossing or plane crossing estimator. Flux tallies are probably the most common type of tally in Monte Carlo calculations, and those are done usually a couple different ways, but track length and collision are the most common. And then the other types of quantities you want to calculate are kind of the degenerate case of the flux. So if you wanted to tally a reaction rate, for example, reaction rate by definition is the integral of flux times cross section. Okay, so if you have the flux already, all you need is the cross section. Same thing with energy deposition. Energy deposition is a kind of degenerate case of the reaction rate. So if you know a reaction rate, then you know how much energy on average these reactions deposit. Energy deposition can be computed as flux times cross-section times what's typically called like a heating function, or how much energy gets deposited on average. So these next couple slides just show the equations for those of you that are mathematically inclined. But basically here on the right is how it's done. So these calculations in Monte Carlo are called tallies because you're just adding things up as they happen. So if you wanted to compute the current across this surface S, what you would do in your Monte Carlo calculation is you would just, every time a particle crossed that surface, you would add the particle's weight to your tally. And eventually, when you finish your calculation, you're going to get a sum here, which is the sum of all the times particles crossed that surface. And the tallies get normalized by the number of particles that you start with, the surface area, if you want to do per square centimeter, and the initial weight of the particles. And you can do this if you think you want to do like ingoing and outgoing, so to speak. You can do it for different values of omega, but really it's just counting the number of particles that cross a given surface. And this is the mechanism we would use for our problem we were just thinking about, which is the transmission versus reflection. If you wanted the transmission case, we would just count the number of particles that cross the kind of rightmost boundary. If you wanted a reflection, you would count the number of particles that cross the leftmost boundary. If the simulation is fully analog, then these W sub i's, these weights, are equal to 1. So this tally estimator just boils down to the sum of 1 every time a particle crosses. So if you have 10 particles cross and their weights are all 1, this would be 10 divided by your number of particles, and that's the estimate of the surface crossing tally. I'm going to go to collision. I'll come back to track length in a minute. Collision scoring is the same idea. So with collision scoring, this is a volume average tally. So you're looking at how many collisions happen in a certain volume. And again, the estimator is just summing the weight at each of those collision sites and dividing it by the cross section. Okay, so weight is dimensionless. Cross section is units of 1 over distance. So, and the V is the volume. So taken together, this has units of number over area, which is flux. That's collision scoring. Collision scoring is good, but the downside of collision scoring is that it requires collisions. So the track length estimator is used more often in Monte Carlo because all it needs to have is particle tracks crossing through a volume. So the particles don't need to collide to score this estimator, because what it does is it sums the track length d sub I, or how much distance does the particle traverse in a given volume. That's your score here. So you're scoring d sub I again times the weight, distance over volume gives units of area. Okay, and this tally results in, again, number per unit area, or flux. Right, so I think I'm going to stop here. We talked a little bit about analog versus weighted. I don't want to dive into those details unless someone has questions. So I'm just going to stop on this slide and say, why do we use Monte Carlo? It's a fairly efficient technique for performing numerical integration in multidimensional problems, and the reason it's valuable is it uses the true data. Okay, so you're randomly sampling from the true physical data, whereas other techniques like deterministic techniques often require averaging or energy grouping for cross sections. The Monte Carlo is a numerical experiment that is based on the true nuclear data. So for that reason, it can be considered more accurate. However, because it's using pointwise data, things like that, you need a lot of data, number one, and a lot of trials, number two. So it is expensive in that sense. Long run times and large memory use make it much slower than other deterministic approaches. However, what you lose in time, you often gain in accuracy. So with that, I'd love to stop and answer any questions that folks may have.
Thank you very much, Dr. Clarke, for the great lecture. We have one gentleman who raised his hand. You can go ahead and unmute and ask your question. It looks like he might have lowered his hand. We have one question in the chat from Sibi. In slide 16, what if the random number generated is exactly at the step of the CDF? Is there any accuracy level in decimal values?
Yeah, it's a good question. I think this was referring to the dice example where I had the step function there, and I think on the slide I had out to 5 decimal places. 1, 6, 6, 6, 7. So eventually you're going to hit the machine precision. So if you imagine a 9 or 10 digit precision there, the odds of hitting those 10 digits exactly are very low, but it can happen. So I think if I were writing the Monte Carlo script, I would put a failsafe that if it were exactly equal to, I would hard code it to just go above or below, right? So kind of just force the rounding in that sense. But again, it's a rare thing because of the precision of whatever machine you're running on. Samuel's hands up again. Should we try?
Yes, thank you for the presentation. That was a well-given presentation. I had a question on slide 26 when you talked about the particle transport problem. And I think my question, might have been answered in the preceding slide on page 34. But I think my question was, if the fate of the particle is, say, like multiple events, because we are defining the energy, we use the energy to sample as one of the sample parameters to define the fate of the particle. If the particle has multiple events where it's either transmitted or absorbed or both, how is that defined in the problem sets? Was this answered on page 34, if I'm not mistaken?
Yeah, kind of. So, a single particle can't really have multiple events, because if it gets absorbed, it no longer exists. If it transmitted, it did not get absorbed. So these are kind of the 3 unique outcomes of any given particle. However, in some situations that were not really considered in this simple example, you can have a source or a secondary event that creates multiple particles, right? So in that sense, you can have, a particle history that ends up, quote unquote, scoring multiple outcomes, right? So that is a subtlety that would get into, exactly what the problem you're trying to solve, and exactly what kind of parameters of the source you're really looking into.
Okay, thank you.
You have another good question from Ben Larson. Using the example of surface area of a target on a dartboard, why would random sampling be preferred over a grid of test points?
It's this. I think we're saying the same thing. So the random sampling is used to create that grid of test points. So, yeah, I guess what it boils down to is how are you generating that grid of test points, right? And as long as that grid is generated in a way that's uniform and unbiased, then either approach would be appropriate.
See a few other questions in the chat. Just a reminder, we have this lecture recorded. So if you need to go back to a slide, please go to the recording link. If you're unsure on the link, I'll drop that in our next email. And then we have another question from Aiden. She's asking, could we include any radiation source in a radiation shielding calculation? And could we add any material composites in shielding material?
Sorry, I just muted that. Yeah, absolutely. So due to time here, I focused on essentially neutrons because that's more conducive to thinking about random walk. But this Monte Carlo approach can be used with anything. So any variable of which you have a physical distribution, you can use these random sampling techniques to sample from those distributions, right? And there's another question about gamma rays. So if you have data for gamma rays, then you can do this kind of sampling in the exact same way. So if I can just indulge myself quickly, like here, for example. So this formulation here is written assuming sigma for neutron transport, right? But if you had mu for gammas, you could do the same type of sampling to figure out what types of distances gamma rays would travel, say, or protons, a bad example, because charged particle transport is handled much differently typically. But yes, the short answer is yes. Any quantity that you have physical data for can be sampled using the Monte Carlo method.
Thanks so much,
software.
Dr. Clarke.
Yeah,
Oh.
I'll just take the last one, and then we'll call it fun. There's one here about software resources. So there are various Monte Carlo softwares that are available. There are open source ones that you can access. GANT4 is probably the most well known. Sorry, GANT4, GEANT4 is probably the most commonly known and used open source Monte Carlo software. But there are many others available. So I just encourage you to do a web search, and you can find several of them out there that are open and available for use.
Thanks again for your presentation,
with
Dr.
that,
Clarke.
Yeah, thanks, Flynn. Thanks everyone for your attention and your questions, and enjoy the rest of your day.